Hello, thank you for joining me today. My name is Taejin Kim. I am a PhD student at Carnegie Mellon University. Today I'll be talking about the project titled Characterizing Internal Evasion Attacks in Federated Learning. This work is planned to be presented at AISTATS 2023. First, we look at the recent growth of distributed machine learning. Distributed machine learning trains a model using multiple computing resources working together. And this has become popular as of late as there has been an increased demand for scalable and cost-effective machine learning solutions. Some examples of tasks that benefit from distributed machine learning include healthcare services, recommendation engines, as well as autonomous vehicles. The work we look at lies between two areas of research. One is regarding distributed or federated learning, while the second is machine learning security. The specific area we are interested in is called defending against evasion attacks in a federated learning setting. We now cover the two key background materials, namely federated learning and evasion attacks. Federated learning is a machine learning process that trains a single global model using many devices and many users sharing data and resources. In a federated learning process, shown to us here on the right, users train a model with their local data and have these models aggregated at a central server. The aggregated model is then given back to individual users for this process to repeat again. Federated learning protects user privacy by keeping the data local and reducing the risk of data breaches. Evasion attacks are a security threat against models and neural networks that may be trained with federated learning. In an evasion attack, an adversary perturbs inputs, in this case an image of a stop sign, to cause misclassification at a victim model. The adversary may leverage a substitute model and its gradient information to perform such an attack. If a model is deployed in a security-critical role, it may cause serious harm. In this example here, an autonomous vehicle is using a model to classify what it is seeing. If a stop sign is perturbed and the autonomous vehicle instead perceives it as a speed up sign, there may be an accident that occurs. We next look at the intersection of federated learning and evasion attacks to propose a novel threat, the internal adversary. All clients that have participated in federated learning end up with the same model downloaded from the central aggregator. If one of these previous participants in federated learning is an adversary that wishes to perform evasion attacks on another prior participant, the success rate of these evasion attacks increase because the model between the two are very similar, if not identical. Our research question is now as follows. How do we reduce the internal evasion attack success rate of these adversarial clients that participate in federated learning? The key aspects in answering these research questions are as follows. First, we want to reduce the similarity of the model the adversary owns and the victim owns, such that the information overlap is reduced. Second, we want to make the victim model innately more robust against evasion attacks. And combining these two ideas together will lead to a good defense. The rest of this presentation tries to explore and combine these two key ideas to make the good defense. First, we'll characterize internal evasion attacks in federated learning and other methods of distributed learning to see how model difference impacts evasion attack success. Then we look at a defense mechanism called federated adversarial training aimed to increase the innate robustness of the victim model. Lastly, we combine the two and come up with a defense algorithm named pFedDef, and we perform an in-depth analysis of it. Let's look at different methods of distributed learning. First is federated average, the traditional federated learning that trains a single global model. Second is local learning, where each client only trains on their own data and no information is shared, leading to every client having a different model. Third combines the first two, personalized federated learning. Here, clients share model information amongst each other, but induce slight differences for each of their models as to better fit their local data and have better performance. In terms of the information the internal adversary has regarding the victim, in the local setting, the adversary has black box information as they don't know anything about the victim's model. In federated average, they have the white box information as they know everything about the victim. In the personalized setting, the adversary has gray boxed or limited information. Our hypothesis is that white box information leads to higher attack success, while it's the opposite for black box. For gray box, the success rate should be somewhere in between. We now look at some empirical results on internal adversaries' attack success rate across these different learning settings. Test accuracy on regular points, not attacks, is the highest for federated average and lowest for local learning, as local learning lacks the information sharing between clients. Internal adversarial accuracy, or robustness against attacks, is the highest for local learning and the lowest for federated average, giving credence to our hypothesis prior. So we see that this accuracy to robustness trade-off exists based on how much information is shared between clients. We further take note that personalized federated learning somewhat transcends this robustness to accuracy trade-off, as it had both a high test accuracy and a higher robustness than federated average. So for the training method or inducing model difference, we use the idea of personalized federated learning. Next, we want to answer the question of how can the victim model gain innate robustness against evasion attacks, and our answer to this is federated adversarial training. Outside of a federated learning context, adversarial training is a process that introduces adversarially perturbed data to the training set for the trained model to take future evasion attacks into account. So in this diagram here, the data is perturbed to include the evasion attack data, and the model is trained using this data that includes evasion attacks. Federated adversarial training combines adversarial training with federated learning. Clients perform adversarial training before aggregation. They have to make their own perturbed data to train over. We perform empirical evaluation, given each of the distributed learning methods when combined with federated adversarial training. Fed average combined with adversarial training increases its robustness from 0 points to 30 points. Personalized federated learning, when combined with adversarial training, we call this defense mechanism P-Fed-Def, and here the robustness is increased from 13 points to 48 points. P-Fed-Def, thus, combines model difference with higher innate robustness of the victim models to maximize its defensive capabilities against internal evasion attacks. And compared to federated average combined with adversarial training, its performance is 60% better relatively. The key takeaway here is that adversarial training increases innate robustness for all victim models, and we found the second ingredient to what makes a good defense, which we call P-Fed-Def. For the last part of the presentation, I want to perform a deeper analysis of P-Fed-Def. The procedure of adversarial training may become a very expensive procedure for specific clients, as the generation of adversarial data points to train over can be very resource intensive. Thus, the algorithm we propose, pFET-DEF, also has a built-in robustness propagation mechanism where clients with more resources generate more adversarial data for training to pick up the slack for clients with limited resources. This becomes especially harder as when clients have limited resources, those that have to generate more to pick up for them must have similar data distributions and thus similar models. We now perform some empirical evaluation on robustness propagation. When resources are constrained, propagation helps increase robustness despite some clients struggling to perform adversarial training. As resources increase in the system, so we're going from left to right on the x-axis on this graph, the orange line and the blue lines eventually converge, meaning that when resources are infinite, the effects of robustness propagation is less pronounced. Now we'll wrap up this presentation. The problem statement we wanted to deal with was the fact that federated learning introduces a new security threat of internal evasion attacks. The solution we propose is called pFET-DEF, the combination of personalized federated learning with adversarial training to enhance the innate robustness of the trained model. The next steps for this project include ideas such as smart local tuning methods to reduce attack transfer rates between personalized clients with similar data distributions and thus similar models. We also want to perform a joint analysis with training time attacks. How does the evasion attack success rate change when certain participants of federated learning perform other types of attacks, such as Sybil or poisoning attacks, simultaneously? Thank you very much for joining me today. Here is my contact information, as well as a link to the GitHub repository of an example implementation of pFET-DEF.